Welcome back. We'll resume our classes now. Okay. So, yesterday we talked about impact against a finite thickness target. Okay. And we looked into the perforation phenomena. Okay. So, perforation phenomena depends upon the interaction between the impactor and the impacting body. If the impactor has a high speed, okay, and or if the target is weak, then there is a chance of perforation. Okay. Perforation simply means when a missile, okay, or an impactor hits a target, and if the target is fully penetrated, okay, then we term this phenomena as perforation. If the penetration is partial, then this phenomena is known as penetration only. Okay. So, here in this figure we can see different examples of penetration. Okay. Let us say if my target material is ductile, okay, then the behavior of the target will be like this. Okay. If my material is having certain amount of toughness, then there might be a radial fracture as observed here. If my material is brittle, okay, then there will be fragmentation. This is normally seen in the case of concrete. Okay. Petling will observe if my target is layered. Okay. Let us say in case of certain composite, okay, layered composite, we will see this type of behavior. One more phenomena is plugging. In plugging, what happens is that when the missile, okay, or the impactor hits a target, okay, and say if it has a protrusion like this, what will happen is that in the first phase, okay, there will be deformation in the missile and it will get flattened out. After that, what will happen is that it will try to punch, okay, like a shear failure, and due to the punching, this plugging will take place. Okay. So, these are the different forms of damage to a target of finite thickness. Moving ahead, what is the ballistic velocity limit? Okay. The ballistic velocity limit, here what we are trying to do is that we are trying to give some key concepts. Okay. One key concept is ballistic velocity terminal limit. Okay. What is it? This is the smallest velocity at which the projectile can still perforate the target. Okay. It means that if, let us say in an example where my target is very thin, okay, it is made up of a very weak material and my impactor is having a very high velocity, okay, then what we are expecting is that in this case the velocity is very high and the material is very weak. Okay. It is very weak and the velocity is very high. What will happen, what we are expecting is that this will perforate. Okay. This will entirely perforate my target material. Let us say that either I am lowering the velocity, okay, I am trying to lower the velocity. Okay. So, what will happen is that there will be a limit, okay, at which it will be just able to perforate this thing. Okay. So, this is the lowest limit of the velocity at which this perforation phenomenon occurs. Okay. So, this velocity is known as the ballistic velocity. Okay. Let us say the initial velocity is V naught and the exit speed is VR. It means that when it enters, it has a velocity V naught, that is the initial velocity, and the exit speed is VR when it comes out. Okay. The corresponding kinetic energies are defined as Ek naught and Ek R. Okay. The initial one and the final one. Okay. So, if the projectile perforates but stops just after, okay, the perforation occurs and the impactor stops out here only. Okay. Then initial velocity equals to VB and Ek naught equals to Ekb. Okay. In that case, my total velocity, my total energy sum is this one. Okay. So, this is the energy balance that we are writing out. This corresponds to the total energy of the impactor initial. Okay. This corresponds to the impactor energy and this corresponds to the final one. Okay. When it comes out, when it is a combination of MP and M. Okay. So, this is the total energy balance. Okay. So, moving with that, if we know the plug mass, okay, in the first case, if we remember, we encountered with this phenomena. Okay. So, this is plugging type of failure. So, we are taking this plugging type of failure. So, let us say we know the plug mass, okay, which we can also assume as the having the same width as the impactor. Okay, we can assume it having the same width as the impactor. Let us say the impactor has a width of d, so the plug mass will have a width of d. Thickness we know, okay, and we can calculate the plugging mass. Okay, so the total expression we can write in terms of Vr, okay, this way. Okay, rearranging the initial term, we can write the velocity of the exit velocity Vr in terms of the masses and the velocity. Okay, so in this way we can also find us Vb and V and the plugging mass. Okay. So here now what we will do is that we will see some penetration equations for different types of materials. Okay. This thing we can find it in Sulazinski's book. Okay. We will give a reference for that also. So we will look into different cases. So we will look into one of the basic material, that is concrete. Okay. In the construction there are 2 or 3 widely used material. One is concrete, one is steel and one is aluminum. Okay. So most of the protective structures are made up of certain combination of concrete and steel. So we are looking into the penetration formulas when a projectile hits a concrete surface. Okay. So these are the empirical formulas. Okay. They have been derived using regression estimates based on some testing that has been conducted in the different parts of the world. Okay. So here, so if we use the AC equations, okay, then my penetration equations are like this, okay, where W and D are the weight and diameter of the striker respectively. Okay. W is the weight of the striker and D is the diameter of the striker. Okay. And the units of x is in inches, velocity is in feet per second, and F prime C is nothing but the characteristic strength of concrete expressed in the SI, expressed in terms of the US customary units. Okay. HP and HS is the spalling thickness of the target, and HP is the perforation thickness of the target, and HS is the spal thickness of the target. Okay. So if you look into the same thing in metric units, okay, so this is the equation in the metric unit where x is in mm, d is in also mm, mass is in terms of g, velocity meter per second, and F prime C is in terms of MPa. So the expression gives x for a plain conventional concrete with hard aggregates. Okay. So this equation is applicable for our conventional concrete, okay, with hard aggregates. Hard aggregate means that we have a sum total of coarse aggregates and we have fine aggregates. Okay. And as per different codes, okay, there is a limitation for this coarse aggregate. Okay. Let us say the impact value, this should be less than 30, okay, and the crushing value should be less than 30. So this, depending upon the different codes, we classify this as hard aggregates. So here this equation we are dealing for the conventional concrete with hard aggregates. The second term is an additional penetration due to the nose of the projectile. Okay. So the second term accounts for the penetration due to the nose of the projectile. This term will vanish when the impacting end is flat. Okay. As we look into, if my impactor looks something like this, then the second term will come into picture. If my impactor is just flat out like this, then this term will vanish. So this term will go to 0 for this type of impactor. So no matter how concrete is, F prime in the equation should not be taken larger than 65 MPa. The reason for this 65 MPa is that because the conventional concrete that we define is around 65 to 80 MPa. Okay. The behavior of the conventional concrete is different from the hardened concrete. Okay. So these equations, okay, when they were developed based on the data that was provided for the conventional concrete. All the testings and everything was done on the conventional concrete. So the behavior of the conventional concrete has been taken into account here. That's why my limitation is 65 to 80 MPa. Okay. In some codes it will be 65 MPa. For this particular equations, these are 65 MPa for the normal concrete. Moving ahead. Now again we are looking into different types of equations. We looked into AC equations, now we are looking into NDRC equations. Basically equations developed by different bodies. Okay. So here again we will see certain other factors also comes into picture. where n is a parameter that accounts for the shape of the nose. So, 0.72 is for a flat nose, 0.8 for a blunt nose, 1 for hemispherical nose and 1.1 for a sharp nose. So, this is a sharp nose, hemispherical nose, blunt nose and a flat nose. Okay. Other things remains more or less same. Okay. So, if we use these equations, we can calculate the penetration depth of a projectile into concrete. So, this thing again is given in US customary units, this thing is given in US customary units and this is given in SI units. Okay. So, depending upon our grade of the concrete and the behavior, we can use any one of these equations to predict my penetration of a projectile into a concrete. The difference of these equations against the equations used in the earlier contact mechanics is that in contact mechanics we used Hertz law and then we use the energy balance. Okay. Here we are directly using empirical equations. So, these are empirical equations. Okay. They have been just made using the test data. So, test data, there is a regression fit of the test data and that is how this equation comes into picture. So, this were test data of the penetration versus other parameters and then one fit has been done. So, this is the difference between the equations used earlier in the contact mechanics which were based on certain law like Hertz law and the energy balance. Again one more equations. So, this is the equation developed by the Sandia. So, these are the national labs in US, okay, where they do a lot of experiments into the blast phenomena, into the impact phenomena and they have a bunch of test data. So, from their test data they have developed these equations. Okay. So, again the first equation deals in the US customary units. Here if we look into this, it has a limitation for the velocity also. Okay. So, when those experiments were done, so they categorized it into velocity, okay, and they kept 200 as a cutting limit. Okay. So, on the left of 200 this equation will come into picture and the right of 200 this equations will come into picture. Why this will happen is that sometimes the behavior, okay, changes with velocity also. Okay. So, the data has been bifurcated into two sets, lower than 200 and greater than 200 and this type of equations has been used. Okay. Again we will see depending upon the weight, okay, the factor K also changes, okay, where weight we know we are using as the weight of the striker or weight of the impactor. Okay. Normally K equals to 1, but when weight of the striker is less than 400, this is the equation for K, okay, and this is the equation for the other factor S. Okay. So, K, S and N. So, 3 factors are being used. Okay. Again we will see some factors are used for plain concrete and FC for RCC concrete. Okay. So, F is a factor 30 for plain concrete, meaning the concrete has no reinforcement, it is just concrete, and F equals to 20 for RC concrete, it means that there are reinforcement present here. So, only conventional concrete, so F equals to 30 and F equals to 20, this is your RCC concrete, reinforced cement concrete. Okay. So, basically what is been done is that the test has been conducted under different conditions, under different velocity conditions, using different grades of concrete, using different configuration of concrete, plain concrete, reinforced concrete. Okay. So, that is why there are different types of equation that tries to fit under different circumstances. The point to remember here is that we need to find out an appropriate equations where whatever we are going to predict or whatever we are going to use for our design purposes, those conditions should be met by this equation. So, we will have to, depending upon our own conditions, we will have to choose the appropriate equation. Okay. So, let us say I have a RCC concrete, okay, the concrete which has reinforcement, then I cannot use F equals to 30, okay, I will have to use F equals to 20, or if my velocity is say 215 feet per second, okay, then this equation will come into picture, not this one. Okay. So, an appropriate equation has to be chosen depending upon in which limit we are there. Okay. So, that is the key to appropriately choose these equations. Okay. So, we will have to be careful also. If you look into certain factors like 0.3, 0.00178, okay. So, these factors are used depending upon the test data in that spectrum also, okay. Depending upon the units, these factors have been used, okay. So, whenever we are using these factors, we will have to be careful that we choose the right set of units also. So, unit matters, the limitations of the equation matters, the conditions in which these equations should be used, this also matters. So, we will have to be very careful when we are using this type of equations. So, for thin targets less than 2D, again, now we were talking about the material properties and the velocity of the impactor. Now, we have a limitation about the target thickness also. Okay. How target thickness comes into picture? If we have a thin target, okay, then it will provide less resistance. Okay. If we have a thicker target, more energy will be required to penetrate it. So, again the format of the equation will change for these two categories. Okay. So, a limitation of 2D has been placed. Okay. So, when the target is less than 2D, means it has certain thickness, then certain value of the coefficient are used, okay, where D is the projectile diameter. Okay. Let us say this is the projectile diameter, and depending upon this, if this is the projectile and the thickness of the plate is expressed in ratio of D. Okay. So, if it is less than 2D, okay, then this will come into picture. Okay. If it is more than 2D, then other equations will come into picture. Okay. Okay. So, again other factors are defined. Okay. Volume of all reinforcing steel, volume of reinforced concrete, TC. Okay. Now, this factor TC is the cure time. Okay. How does TC comes into picture? Okay. TC is defined as a cure time. Okay. We know that concrete gains its strength over a period of time. Okay. Normal concrete gains its 66% of strength in around 7 days. Okay. The normal strength of the concrete that we consider is 28 days, but after 28 days also it keeps on gaining strength. Okay. And in case of certain type of concrete, okay, like our hardened concrete, okay, a concrete having very high strength, okay, so that will keep on gaining weight across the years. Okay. Down the line 3 years, 4 years, 5 years, it will keep on gaining strength. So, if the target keeps on gaining strength, okay, it will provide more resistance to my impactor. So, the penetration depth will be less for a concrete which has gained more strength. Okay. Here the point to remember is that we are taking into account the property of the concrete to gain strength over period of time. Okay. So, we are taking into this property. Okay. Here the degradation in the concrete owing to other factors, other environmental factors has not been considered. Okay. So, TC is the cure time expressed as a fraction of 1 year. For older concrete, TC is taken as 1. Okay. Again, capital TC is the target state expressed as a multiple of T, that is the projectile diameter that we explained just now, and F prime C is the unconfined concrete strength at test time. Unconfined concrete strength means that when the concrete was tested, either it was tested as a cube or it was tested as a cylinder. Okay. So, if we look into our Indian codes, we define it as FCK. If we look into the American codes, it is defined as F prime C. Okay. So, whenever we hear the term FCK, it means that we are testing a cube, and whenever we hear the term F prime C, it means that we are testing a cylinder. Okay. So, and these two properties are interchangeable. There are factors associated where we can change from, if we have been given F prime C data, we can change to FCK and vice versa. Okay. And this is the configuration of the projectile. Okay. So, here D is there, B prime B, etc., all those things are given. Okay. So, depending upon this thing, we can use our appropriate equations. Okay. And for our shape of the nose, okay, so for different nose shapes, the value corresponding equations for n is also given. Okay. So, This is a tedious process, but since this process comes from certain curve fitting of the experimental data, it gives a more reliable result. Okay. Though the equation looks very cumbersome, okay, but the accuracy of this equation is higher, okay, because these are based on the actual test data. The only problem associated with this type of equation is that they are only good in the range in which they were calibrated. Okay. If we come out of that range, the equation might not be predicting the actual penetration. So, the care has to be taken when this type of equations are being used. Again, moving ahead. Okay. So, now different other parameters are trying to be expressed. Okay. We were looking into the penetration depth, now we are looking into the radial stress. Okay. And this is the condition under where radial stress during spherical cavity expansion as a function of the expansion velocity. Okay. So, V1 square we are defining as the initial tunneling velocity. Okay. Sigma c is the effective medium stress, n is the factors, and x is the penetration depth. Okay. So, for different grade of concrete, okay. So, for the different grade of concrete, the corresponding parameters were used. Okay. So, this is one example, okay, where we can use the equation to predict the penetration. Okay. So, grade of the concrete, this is again grade of the concrete, density of the concrete, okay, and properties of the concrete are used, and then we can calculate the stresses and the penetration depth. Okay. And this is given for an ogive type of nose projectile. Okay. The shape of the projectile looks like this. Okay. So, it has this type of properties. So, moving ahead again in this topic, now we are looking into the design aspect. Okay. So, we are looking into the minimum concrete thickness necessary to prevent perforation. Okay. This is the term XP. XP is defined as the minimum amount of concrete thickness necessary to prevent perforation. Perforation means the total penetration of the projectile into the target. Okay. If X is the maximum penetration of the same projectile into a very thick slab. Okay. Let us say we have this type of impactor. Okay. It is coming with a velocity V0. Okay. The dia is this much. Okay. And what it is going to do is that it is trying to penetrate this concrete. Okay. So, in concrete we will see, we have already seen some sort of fragmentation will occur, a plugging type of mechanism will be formed, and here the punching will also start. Okay. So, these are the typical damage zones that we define. Okay. So, this is true for a normal type of brittle plate. Okay. It can be made of concrete or it can be made of other brittle material also. Okay. So, this type of damages will be observed in a brittle type of material. Okay. So, what will happen? So, we will try to see the different zones. So, near the impact point, the surface damage has a form of crater. Okay. This zone, okay, where sort of punching and crushing, okay, both are trying to happen. There will be a crushing. Okay, if it is concrete, if it is other type of material, then there will be a surface damage also. So, here some sort of crater formation will try to take place. Okay. So, this crater will depend upon the diameter of the projectile. Okay. So, what it will try to do is that it will try to form some indentation, or if it is a type of metallic brittle material, and if it is concrete, it will try to form also, it will try to, here the compressive failure will also occur. Okay. So, here crushing will also try to form. Okay. And this crater diameter, okay, this crater diameter will be related to the configuration of the impactor like this. Okay. The motion after this thing past the crater is known as tunneling. Okay. See what it is doing, it is trying to form a surface like this. Okay. So, the motion past this crater is termed as a tunneling. Okay. So, finally, what will happen is that at a distance of h star from the back surface, a cone of material is pushed out, forming a rear crater. Okay. So, one crater formation will try to take place here also. Okay. If it is concrete, we will see fragmentation also. Okay. If it is other bitter material, we will try to see this type of plugging material also. Okay. So, in tunneling, we know that tunneling, what happens is that impactor, okay, or a drilling type of machine tries to punch out hole from both the ends. Okay. So, here also we will see large indentation occurring, here also see plugging occurring. Okay. So, this whole thing is termed as a tunneling phenomena. Okay. So, front face also will undergo this type of deformations, the back face will also go under this type of deformations. Okay. So, here this thing will be tried to push out, okay, and here this thing will be pushed in. Okay. So, rear crater and the front crater. Okay. The initial cratering or the tunneling stage may not be clearly shown if the plate thickness is too small. Okay. If the plate thickness is too small, then this will coincide with this much. Okay. So, we cannot make out the proper tunneling process. If the thickness is large, then this two type of phenomena will independently show up. Okay. Now, we are defining the plug resistance, okay, resistance of the plug as Fp, and the angle is defined like this. Okay. And the expression for the plug resistance is defined like this. Okay. The material properties comes into picture is the tensile strength according to the molecular criteria. Okay. To find this H star, okay, and this is one of the drawback of this empirical equations, we need some sort of experimental data in order to calibrate my H star, okay, or the depth in which a material behaves and a crater tries to form out. Okay. So, moving ahead. Now, we will look into a case where we know that for a particular concrete plate, the thickness to prevent that penetration is known. Okay. It means that we know the final answer. Okay. Let us say XP we have defined as minimum concrete thickness to prevent perforation. Okay. This was the definition of XP. Okay. So, the minimum, suppose for a particular concrete plate, the thickness to prevent penetration is known. Okay. So, the XP is known. In that case, where the actual thickness of the concrete slab H is smaller than XP, the residual velocity of the striker may be calculated from the equation provided by TM 1300. Okay. So, these are the equations given by TM. So, again VR and V initial, okay, and H and HP. Okay. So, here we can see that these equations are again empirical equations. Okay. Here we can only see the geometric properties, but the inside the behavior of the material is inside this expression of XP, okay, which again in turn are related to my depth of the penetration. Okay. So, this way we can correlate the things. So, I will stop here.